In math class, I hated being told what was true without being told why it was true. And one of those facts was that the trig functions, sine and cosine, are continuous. You can see that visually, sort of, but what if my eyes are deceiving me? What if there are holes in the graph that I can't see? I wanted more justification, and we're going to look at that in greater detail today. But before we can tackle that question, we need to agree on what sine and cosine even mean. So just as a recap, in high school, you were probably given a right angle triangle and you're told that sine of theta, sine of an angle of that right angle triangle is the opposite side length divided by the hypotenuse. And you're told similarly that the cosine was the ratio of the adjacent side length and the hypotenuse. Well, let's make it easier. Let's take h to be 1, and let's call this vertex over here V, and let's pin V down. And we can imagine rotating H around. And what do we get? Well, it's H is just a length 1 line, and we rotate it around. We get a unit circle. And in fact, any point I pick on this unit circle, let's call it xy, I can trace or I can find an h that got me to that point. That has length 1. And then I can drop a perpendicular to find a right angle triangle there. So in fact, x and y are really just, well, let's label that angle, are cosine of that angle and sine of that angle, respectively. Okay, so this is what I'm going to define my sine and cosine to be. It's the x and y coordinates of a point on the unit circle, or the ratios of these triangles, respectively. And we're always going to take the hypotenuse to be length 1. Okay, so before we try to address the whole problem of continuity, let's go ahead and check that the limit of sine of theta as theta approaches 0 is indeed 0. So that's sine of 0. Oops, not sine of theta, sine of 0. And how are we going to do that? Well, it's not obvious because we can't just plug it in because that would be assuming a conclusion. We don't want to just assume that sine is continuous to check that as continuous, right? So it's not obvious what we can do. We can't really use limit properties because sine doesn't behave very nicely. So we're going to call in an old friend, which hasn't seen a lot of light, which is the squeeze theorem. So let's draw a little picture here. Let's pick an angle, and I'll do a positive angle, but it works same for a negative angle. So let's do a theta here. That length is 1. We're always taking the hypotenuse to be length 1. And, oops. And we have a right angle over here. So this length, we can imagine the part of the unit circle here that extends. So part of unit circle, or arc of unit circle, let's say. And we can compare that with this length. So arc length, the blue arc length should be greater than the orange length, which is the opposite side. And that's, maybe I should use length so I don't confuse you with 0. And that should be greater than or equal to 0. Okay, so now all we have to really do is figure out what these lengths are. Well, we should know that the orange length is actually just sine of our angle. That's what we looked at in the last part. Because our hypotenuse is 1, the orange length is just sine of our angle. And because of the way that circles work, the arc length is just going to be the, well, we can write it as the whole circumference, for example. So 2 pi times the radius multiplied by the amount of angle coming from theta. So we can multiply that by theta divided by 2 pi. But r is 1, and we can cancel off our 2 pi's. So we actually just get that the arc length is theta. So in fact, we get this inequality, this nice inequality here, that 0 is between sine of theta and theta for positive angles. But if we want to include the negative angles, it works sort of the same way, but with the inequalities flipped. So what I'm going to do instead is write them with absolute values. So this is going to be the absolute value of sine of theta is less than the absolute value of theta. Okay, but the limit as theta goes to 0 of 0 is 0, and the limit as theta goes to 0 of the absolute value of theta is also 0. We can appeal to the continuity of the absolute value there. So the squeeze theorem says the limit as theta goes to 0 of the absolute value of sine of theta is 0. But since that limit is 0, we actually also get that the limit as theta goes to 0 of sine of theta is 0. Note, I can't just take off the absolute values in general, but because this limit is 0, I can. If you don't like to do it this way, you can also do it with two-sided limits, and that's fine too. You have to use the squeeze theorem twice. Okay, so let's check that. I've graphed absolute value of x in red. Here is the absolute value of sine of theta. And in blue, we have just y equals 0. So indeed, sine of theta is being pinched or squeezed between 0 and the absolute value of theta. Just in case we needed some visual confirmation that what we were doing up here was indeed true. So we just checked that the limit as theta goes to 0 of sine of theta is in fact 0. And from this, we can actually get that the limit as theta goes to 0 of cosine of theta is 1. So how do we do that? Well, I'm going to use the fact that we're on the unit circle. So we get the Pythagorean identity from that. In other words, that cosine of theta squared plus sine of theta squared is always equal to 1 for any theta. So I can rearrange and get that cosine squared of theta is 1 minus sine squared of theta. Okay, but for theta, absolute value of theta less than, let's say, pi over 2, I can actually just take a positive root because I know that cosine is positive. So cosine of theta is actually just the square root of 1 minus sine squared of theta. And that means that the limit as x goes to, or let's say theta, let's keep consistent here, as theta goes to 0 of cosine of theta should be the same as the limit as theta goes to 0 as the square root of 1 minus sine squared of theta. But I have that polynomials are continuous and root functions are continuous. So I can plug this limit in. So this is going to be the same as 1 minus the limit as theta goes to 0 of sine of theta squared, which is just the square root of 1 minus 0 squared, which is just 1. And now that's a verification that the limit as theta goes to 0 of cosine of theta is 1. So cosine is continuous at 0. Okay, but how do we get this continuity in general? We just checked one point. If we checked every point individually, we would never be able to do it. So what I'm going to do is a slightly different notion of continuity. It's equivalent, but it looks slightly different. And the reason why I'm going to use this formulation is so that I can use trig identities that we learned in high school. Okay, so I really just want to check that the limit as h goes to 0 of sine of x plus h is just sine of x for any x. Okay, let's verify that. So limit is, h goes to 0 of sine of x plus h. Well, that should be the limit as h goes to 0 of, okay, well, now I have a compound angle in my sine. So I can use my compound angle formula. So that's going to be sine of x cosine of h plus sine of h cosine of x. So what did I do here? That's my compound angle formula for sine. And because x is fixed, I can use my limit properties because sine of x, so x is fixed, so sine of x is a constant, and cosine of x is a constant. So I can use my limit properties to say that this should be sine of x times the limit as x or as h goes to 0 of cosine of h plus cosine of x times the limit as h goes to 0 of sine of h. But we just calculated these, so we can evaluate these now. So sine of x times, well, what's this limit of h going to 0 of cosine of h? We saw that that was 1 plus cosine of x times this limit of sine, but we saw that that was 0. So in fact, we're just left with sine of x. So sine of x is continuous on R. because we just checked it for an arbitrary x. So that means it has to work for every x. Awesome. Okay, so can we do the same thing with cosine? And of course we can. It's the same argument, actually. We just use the compound angle formula for cosine instead. So let's run through those details quickly here. So we're looking for the limit as h goes to 0 of cosine of x plus h. And now we want to invoke our compound angle formula, which says that that's equal to cosine of x times cosine of h minus sine of x times sine of h. So again, this is compound angle formula for cosine. And for the same reasons as before, x is fixed, so I can treat cosine of x and sine of x like constants and use my limit properties. So this should be the same thing as cosine of x times the limit as h goes to 0 of cosine of h minus sine of x times the limit as h goes to 0 of sine of h. And we already know what those are. We can plug those in. So cosine of x times 1 minus sine of x times 0. And we're left with cosine of x. So indeed, cosine of x is continuous on the whole real line. So we've just justified why sine and cosine are continuous functions. And it does indeed follow that functions like secant and cosecant and tangent and cotangent are all continuous. Why? Because they're just quotients of sine and cosine. So except for those points where we're dividing by 0, those functions will be continuous too.